So let's see if I can get this done during my lunch break. All right, population growth of Boomtown is shown in the accompanying graph. Now, a couple of things that stick out. When I look at this graph, what I see is I see exponential growth. Okay, that's what I see. If the same pattern of growth continues, what will the population of Boomtown be in 2020? And it's going to be more than this line. It's going to be up here somewhere. All right. I don't know exactly where, but the slope is increasing. It's called Boomtown. But I saw exponential growth. So what we're going to do is we're going to take our things, we're going to create ordered pairs. Like this is 1980 and 2. Then we have 1990 and 4. And this is probably in thousands, right? So it's 1990 and 4,000. You don't have to write the 4,000. Then we have 2000, and what's the other ordered pair here? 8, 2010, and 16. And I have stuff that I can put into list 1. It's x's into list 1, y's into list 2. So I'm going to throw this at my TI-84. Of course, you had to understand you had exponential growth, and just, I don't know why I'm at y equals. But stat, edit, clear. I just don't know what to do. Y'all resist it. You don't want to know it, so therefore you choose not to know it. It's the only thing I can come up with. I wish I could make you love the content. If you love the content, it would come so much easier to you. For those of you who understand, when I look at it, that it's exponential growth, good, because that's what you're supposed to do. You're supposed to look at something and know what it is. Is it linear? Is it non-linear? What does it look like? That's what this stuff's about. So I've got my points in. I'm going to quit out. And I thought it looked like an exponential regression, so stat calc. I'm looking for exp reg. There she is, exponential regression. And calculate. And it's going to give me an equation. And it's got some teeny tiny numbers. Now, let me show you something I can do that'll make that a little bit different. The reason these numbers are so god-awful is because I use 1980, 1990. I could have used 0, 10, because 1990 is 10 years after 1980, 20, and 30, because 2010 is 30 years after 1980. So stat, calc, went too far there. Didn't go far enough. There it is, exponential regression. And I'll get better looking numbers this time. Didn't have to do that, but the equation's a whole lot easier to write, isn't it? So think about little things like that. Here's my equation. So let's write this out, insert text. It is y equals 2, because that's the first term, times 1.07, let's say 2, to the x. And I'm going to write a little disclaimer here, okay? Where x is the number of years after 1980, because that's what I chose to do, to make the equation look better. Now, some of you guys are just blindly clicking through and you're not listening to subtitles, and you have no idea that I changed the x values. You have no idea I did that. So that's on you. So if I want to know what population of Boomtown is going to be in the year 2020, well, 2020 is, I can't even type, is 40 years after 1980. So I'm just going to feed this thing a 40. Y equals 2 times 1.072, rooftop to the 40. And let's see what that is. 2 times 1.0. The more decimals you keep, the more accurate your result shall depending on how you round, depends on your answer. 32.272, and that's in thousands. 32.272 thousands. So the reason I went out 3 decimal places is so I could say this: 32,272 citizens. And I got pretty close. Like, I figured just by looking at pushing a dot that it'd be around 30. just by kind of thinking of how the slope would change. But I have a lot more experience of this stuff than y'all. And I'm still wrong sometimes. So anyways, population of a small town over 4 years recorded in the chart below, where 2013 is represented by x equals 0. So that's going to be 0, 1 year after, 2 years after, 3 years after. Okay, kind of the same idea as before. The population P of x for these years can be modeled by the function P of x equals a times b to the x, where b is rounded to the nearest thousandth, that's third decimal. Which statements about this function are true? Now, a is going to be, it's the initial population. That is a given. A is going to be 3810. So I don't even need a calculator to tell me that, but I'll do one just so you can see. Let's go to stat, let's go to edit. Clear out our list and push some more buttons. So the way this has always been is that the first row is list 1. I do not foresee that being changed on you. If you don't understand that, it's because you just really haven't been trying. The second one, the second row is always going to be list 2. Now, they don't tell you, they tell you it's exponential. Y equals a to b to the x is exponential, which is something I should probably write down because you don't realize that. But the form they're giving you is exponential growth, that a times b to the x is exponential. Some of you, I don't know what's going on in your head, but that is exponential. So I'm going to do the exact same type of regression that I just did. I'm going to go to stat. I'm going to go to calc. I'm going to look for EXPREG, exponential regression. And I'm going to scroll down to calculate. And there's my equation. Now, the calculator has rounded, but it looks a lot like what I was telling you. They do want you to round to the nearest 10,000th position. Okay, so if you write your equation, it's y equals 3809.869 times b, which is 1.035, and then it's rooftop to the x. I still have a r on, but that's only for lines, so it doesn't really matter. So anyway, which statements are true? The first one, like I told you. And look at B, right there. So 1 and 4. Easy peasy, lemon squeezy. All right, 19. 170 DHS males were found to have a mean height of 68 inches with a standard deviation of 2.25 inches. Use the 68, 95, 99, 7 rule to find the following. The room is there for you to draw. So, you're expected to memorize this guy. And it's going to be bad. So the mean's in the middle, it's 68, and you're going to add 2.25, so 70.25, and you're going to add it again, 72.5, and you're going to add it one more time, so 74.75. You're going to take it away 3 times, because that's how we do it. This would be 65.75, 63.5, 61.25. And you need to memorize some numbers here. These are 34 and 34. Now, what I will do is I will give you a incomplete bell curve. And I'll show you what I'm going to give you. I will give you something looks like this. Up top and on top, it'll say 68, 95, 99.7. I'm not going to give you all the stuff in the middle. I'm going to give you exactly what the state gives you, and the state gives you that, and that's what I'm going to give you. All right, find the percentage of males less than 63.5 inches. So that would be those two sums, okay? 2.35 plus 1.5. which is going to be 2.5%. Not hard. Percentage of males between 68 and 72 and a half. That's going to be that guy, and that guy. That's 34 plus 13.5 plus 2.35, which is 43.85, I think. Seems right. No, God, no. 49.85. I am off. Ugh. It's not the eraser. Okay, so 34 and 13 makes 47. 47 and a half, 49 and a half, 49.85. Percentage of males 2 standard deviations above the mean. So I go over 1, 2, and I'm interested in this information right here, 2.5%. You really have to develop an intimate understanding of the bell curve. The last part, part 4, the number of males with a height between 61 and a quarter and 63.5. So that's going to be those two. 2.35 plus 13.5, which is 15.85. I don't think there was another one. I feel like there might have been a choice 5, but it's not there, is it? All right, so we're good on that. All right, these are done using a TI-84. I'm also out of time, which sucks. So I would love to keep doing more, but I ran out of time.